low energy neutrons and they get scattered by hydrogen. So I assume hydrogen, well, the hydrogen molecules probably, but it's the nuclei that's scattering them. Okay. So and what you actually observe is the S wave. So the little L0. That's what we've been talking about in these sessions. So the S wave cross section, this here, is much larger than the known range of interaction, like the range of the, well, we're talking the nucleus, the range of the strong force, which is of the order of a few femtometers, 10 to the minus 15 meters. Right? So if you model the nucleus as a kind of hard sphere, in other words, the potential inside the sphere is like infinite, so you can't penetrate it. It's impenetrable. We've talked about models like that before, okay, with bound states and so forth. Okay, so the size of the nucleus, a few femtometers, 10 to the minus 15 of the meters. So if so, this cross section here is much larger than that range, or if you like, the area of interaction, which would be the cross-sectional area of the nucleus, which was just pi r squared, and r, the radius of the nucleus, is a few femtometers, if that. Okay, so the cross-section is much larger than that pi nuclear radius squared, right? And it's thought, this phenomenon is thought to occur due to a bound state of deuteron. Now, what deuteron? Deuteron is a special case of hydrogen. Hydrogen normally just has one proton in the nucleus, but deuteron has one proton plus one neutron. So two particles in the nucleus. And where these two particles are sort of rather weakly bonded, whatever that means. You're talking about the strong force. Okay. All right. Now, there's only a little bit of theory left for this chapter, and I didn't quite have enough board. I could have gone on to a whole new quarter board, 2 squares, but it was hardly worth it. So I filled it up as much as I could, and there are only just a few more lines left. So I will give those the next session combined with the problem solving. So now we do, in a sense, the other case. Two sessions previously, we were talking about I'm looking at the board because it's still there, but you can't see it. Previously, we talked about the attractive spherical whirl in the limit of low energy S-wave scattering. Well, now we're doing the opposite. Now, instead of being attractive, it's now repulsive. So we change the sign of the potential. Okay, so that's an attractive potential. We're still talking low energy S-wave scattering, so little L0. Okay, so we change the sign of the potential. So now we've got a repulsive potential, and let's assume that this V0 here, the size of the repulsive potential, is larger than E, and we do that because then we can let V0 become very large, and in the limit it just becomes a hard sphere, right? Impenetrable. Okay. Well, pretty well all the analysis we did in the previous sessions carries over. So there are just a few changes, like this now differs. So various big K changes. So we do the usual, the same stuff as before. We do the matching, right, at the boundary. At the radius r is little a. You match the two values of the wave function. You match the two values of the gradient of the wave function at that boundary r equals a. So that's what I'm talking about when I just say matching. So you do the usual matching technique that you've done quite a few times now. Right? Now, so this time your capital K here is a bit different because you've changed the sign of the potential. Right? So you have a different capital K here, and this capital K with repulsive potential of your nucleus, or your target, your scattering source. So your capital K now is defined this way, right? So 2 mu into V naught minus E, that's the difference, divided by h bar squared. And you go through all the same stuff and you solve for your delta naught, just the same way you did before, but with slight differences. When you match gradients and values of the wave function, you'll get, I think that's the same, let me just check, I think that's the same. Yes, that's the same. And this now has a than instead of a tan, and the K will be a bit different. Alright? So derive this, I could put that as homework, I guess. I'm curious to know just how many of you are actually studying these courses seriously, in the sense of doing the homeworks. I don't know, maybe it's a bit premature. I don't have enough courses videoed yet to be able to make a strong appeal for the creation of grading centres to use these courses. I mean, I'm only halfway through the second course. It's probably a bit premature. Anyway, so okay, so you have this relationship where your new capital K has K squared takes this value. You can solve for your delta naught, your phase change, and you get this, which is fairly similar to what you got before, except before you got a tan, now you got a than, and the capital K is different. Alright, once you've got your phase change, your delta 0, you can find the value of the cross section by using this formula, right? And that will give you your total cross section, and from that you can predict how things will scatter. Now I still have a few more lines in the theory. I'll do that. Run out of board for this session. I'll just finish those few lines. Finish off the next session, combined with problem solving.